Can I begin? Okay. So this is a joint work with Shiri, Chechik. Now let's skip problem definition and literature review. Similar to the previous group, we also need to define the notion of random greedy MIS. So suppose we are given random order pi over all of the vertices. So we go over each vertex in this order pi and add it to the MIS if it is not yet dominated by previous MIS vertices. For example, in this graph, we would add the first vertex and then the fourth, the fifth, and the seventh vertex to this greedy MIS. So the main theorem says we can maintain a greedy MIS with respect to pi with expected polylog time. Our algorithm uses two building blocks from previous works. And the first is what we call a degree reduction lemma. Let U be the set of vertices not dominated by vertices by MIS vertices whose rank are less or equal to k, where k is an integer. Then this lemma says the induced subgraph on these set of vertices U has maximum degree at most n over k. So pictorially speaking, suppose we divide the set of all vertices into two groups using this threshold k, and consider all MIS nodes on the left-hand side, and they might be dominating vertices on the left-hand side. After removing these vertices, and then we can collect an induced subgraph on the remaining ones with maximum degree at most n over k. And the second is a structural lemma by Kern-Hill in 2016. Suppose there's an edge update between UV in this graph. It is an edge deletion. We define the following influenced set. We grow this set by adding all of the MIS successor to this set. And inductively, we add two kinds of vertices to this set S. The first kind is all non-MIS vertices whose MIS predecessors are already in this yellow area. For the second kind, we go over each non-MIS vertices in this set S, and we add all of its MIS successors to this set. We can prove that any change to the greedy MIS incurred by this edge update are within this yellow area. So the lemma says the expected size of S is bounded by a constant. Here's a sketch of the main algorithm. For every power of 2, 2 to the b, we explicitly maintain the induced subgraph, GB, of all vertices not dominated by MIS nodes of order less or equal to 2 to the b. So basically our algorithm does two things. Suppose there's an edge update. Then in the first step, we compute the influenced set. And then we compute vertex updates to subgraphs. Now let's discuss more details. In the first step, suppose, well, in this example, there's an edge insertion between U and V. And suppose we have inductively computed part of the influenced set. Then to grow this set larger, we go over newly added vertices. Let's say this is an MIS node at position 2 to the ith. Then we scan all of its neighbors in the subgraph, and for each one of them, we check if all of its MIS predecessors are already in S, and if so, we add it to this set S. So in the second step, we need to update induced subgraphs. Suppose we have flipped some MIS vertices in the yellow set, and so there might be dominating some non-MIS vertices in the subgraphs. So by definition, we need to remove these vertices from those subgraphs. Okay, here's a sketch of the analysis. So suppose both endpoints of the edge update are between 2 to the b and 2 to the b plus 1. So we want an update time of at most n squared over 2 to the 2 times b. Basically, suppose there's an edge update within this interval. So using the previous lemma from by Kern-Hill et al., we could somehow argue that the expected size of S within this interval is bounded by a constant. Let's say this is 1. By generalizing this a bit, we can prove that the expected size of S within this larger interval is bounded by 2. So basically, this is because with probability half, this edge update is within the first interval. So the conditional expectation can be bounded by 2. More generally, we can argue that the expected size of S within this very long interval is bounded by 2 to the I minus b. So the total number of vertex updates to subgraphs can be bounded by n over 2 to the b. So basically, when I is small, where each MIS update could be expensive, there are not too many of them. And so the total work can be bounded by n squared over 2 to 2 times b. Now let's unpack more details. So by extending this lemma, we could argue an upper bound on the size of S. So the hard part becomes the total number of vertex updates. But the trivial upper bound says it is bounded by the maximum degree times S. So for the update time, it could be too large. Now let's refine this upper bound by looking at each vertex within the yellow area. Let's say it is at position 2 to the ith. Then we have an upper bound. We have a handle on the degree of this vertex. So the size of this green set is bounded by this summation. Therefore, if this yellow set is evenly distributed along this axis, let's say it behaves like a random subset, then we can kill this extra maximum degree factor and replace it with a logarithm, and this would give us the desired bound. So in summary, the key to the analysis is we need to study how this set S is distributed along this axis. Namely, although in the worst case, the set S could be packed entirely within this very narrow interval, we argue that in the average case where S is evenly distributed is the more common case. And yeah, that's all.